All right, let's talk about one of the craziest, most mind-bending ideas in all of modern physics. We're going to dive into a single paper from 1997 that, no joke, completely changed the game. It floated this wild idea. What if our entire reality is just a hologram? Yeah, you heard that right. Let's get into it.
So just think about this for a second. What if everything you see, this whole complex, three-dimensional universe with all its gravity, what if it's all just a shadow, a projection, like a super advanced hologram being beamed from a much simpler, flatter world, a world that doesn't even have gravity? Sounds like something straight out of a movie, right? Well, a major paper from the 90s made a very serious case for it.
So yeah, back in 97, this physicist, Juan Maldacena, drops a paper that sends shockwaves through the physics world. I mean, it was a huge deal. What he did was build this incredible mathematical bridge. He connected two totally different theoretical worlds that, honestly, nobody thought had anything to do with each other.
Okay, so to really get what he did, you gotta understand these two worlds he connected. You can just call them World A and World B. And trust me, they are like night and day.
So in one corner, you've got the particle world. Picture a flat, lower-dimensional place. It's all about particles and forces, described by something called a conformal field theory. But here's the kicker. There's absolutely zero gravity. None. Then in the other corner, you have the gravity world. This place is the total opposite. It's higher dimensional, and it's all warped and curved. Physicists call this anti-de Sitter space. And here, gravity is the star of the show, along with all the complexities of string theory. So you have these two universes that are completely different. How in the world could they be related? Well, the secret sauce, the thing that makes this whole connection work, comes from string theory. It's a concept that's, well, it's pretty weird, but it's also incredibly powerful. It's called a D-brane. Okay, so what on earth is a D-brane? Let's keep it simple. Imagine it's like a sticky sheet of paper floating around in space. In string theory, you have these tiny, vibrating open strings, and their ends are literally glued to this D-brane. They can't leave it. And this is where Maldacena's genius really kicks in. He realized you could look at a whole stack of these D-branes from two completely different points of view.
And this is where the magic happens. Okay, so first, imagine you're looking at this stack of D-branes from really, really far away. You're in what they call the low energy view. All you can see are the little strings wiggling around and interacting on the branes. And you know what that looks like? It looks exactly like our particle world, a system of quantum particles with no gravity. But what if you zoom way in? When you get up close, you have to account for the fact that this stack of D-branes has a ton of mass and energy. And what does mass do? It warps spacetime. Suddenly, you're not looking at particles anymore. You're looking at a curved, warped geometry. You're looking at the gravity world. See? Two different views of the exact same thing.
Now, here's the thing. Physicists had known for a while that you could describe these D-branes in these two different ways. It was a neat trick. But what Maldacena did in his paper was so much more than a neat trick. He made this absolutely radical claim. He said, hey, what if these aren't just two different perspectives? What if it's something way, way deeper? And this quote right here, this is the heart of it. He formally conjectured that these two descriptions are dual to one another. Now, in physics, that word dual has a super specific and powerful meaning. It doesn't just mean related or similar. It means they are mathematically identical, 100% equivalent. So let's just let that sink in. What he was saying is that the simple, flat world of particles and the complex, curvy world of gravity, they aren't just connected. They are the same thing. It's like having the same story written in two different languages. The words are different, the grammar is different, but the meaning, the underlying reality, is exactly the same. And this bombshell of an idea got a name, the ADS/CFT correspondence. It's the formal statement of this duality. It says that a theory of gravity inside a volume of space, the bulk, which is that curved ADS space, is completely identical to a quantum theory of particles living on the surface or the boundary of that space. So all the complex gravitational stuff happening inside is somehow perfectly encoded on the simpler, flat boundary. Okay, so this is mind-bending stuff for sure, but you might be asking, so what? Why did this paper become one of the most cited papers in the history of physics? Well, because it's not just a cool philosophical idea, it's an incredibly powerful tool. Yeah, think of it like the ultimate Rosetta Stone for physics. It's a dictionary that lets you translate any problem from the language of particles into the language of gravity, and vice versa. And this isn't just any dictionary. This one has a superpower. The superpower is called a strong, weak duality. And what that means is something that is ridiculously complicated and hard to calculate in one world becomes simple and easy in the other. It's wild. For example, trying to figure out the behavior of the quark-gluon plasma, this incredibly chaotic soup of particles from the early universe, is basically impossible using standard particle physics. But using the duality, you can translate that problem into the gravity world. And guess what it becomes? It becomes a pretty straightforward problem about a black hole. You solve the easy black hole problem, translate the answer back, and boom, you've just solved an impossible particle physics problem. It is literally the ultimate physics cheat sheet. Okay, there is one important catch here. This magic dictionary works best under a specific condition, which Maldacena points out right in the title of his paper. It's called the large N limit. That N is just the number of D-branes we were talking about. When N is huge, like really, really big, the gravity side of the dictionary becomes super simple and reliable. You can think of N as being like the pixel count of your TV. The bigger the N, the sharper and more high definition your hologram is. All right, so let's bring this all the way back to the big question we started with. Does this mean our universe is actually a hologram? Well, the honest answer is not exactly. See, Maldacena's amazing discovery applies to a very specific theoretical kind of universe, that anti-de Sitter space we talked about. It's not our universe. But, and this is a huge but, what it did was earth-shattering. It was the first ever concrete mathematical proof of something called the holographic principle. It showed us, without a shadow of a doubt, that a universe with gravity can emerge from a simpler, lower-dimensional world without it. It completely changed how we think about the very nature of space-time and reality itself. So here's the bottom line. Maldacena's work didn't prove that our universe is a hologram. What it did was prove that a holographic universe is a real mathematical possibility. It's not just sci-fi anymore. He opened a door that can never be shut again, and it leaves us all with a pretty profound question to chew on. What is reality, really?